In November 2024, 4 human beings travelled farther from Earth than any humans had travelled in more than 50 years. Not to the Moon's surface, the Artemis II mission was a free return trajectory, a loop around the Moon and back, the same basic path that Apollo 13 flew after its oxygen tank exploded in 1970, the path that allows a spacecraft to use the Moon's gravity to redirect itself back to Earth without requiring a powered burn at lunar distance. The crew of Artemis II, Reed Wiseman, Victor Glover, Christina Cook, and Canadian astronaut Jeremy Hansen, travelled to a maximum distance of approximately 9,000 kilometres beyond the far side of the Moon, reaching a total distance from Earth of approximately 450,000 kilometres at the furthest point of their trajectory. This made them the humans who had travelled farthest from Earth since the Apollo 17 crew returned in December 1972. More than 5 decades. An entire generation, in some cases 2 generations, during which no human being had left low Earth orbit. And now 4 people in the Orion spacecraft were passing around the Moon and looking at something that no human eyes had seen from this perspective in living memory. The far side. The lunar far side is one of the most alien places accessible within human reach. Not alien in the science fiction sense of strange creatures or exotic chemistry. Alien in the specific sense of being profoundly different from anything observable from Earth. Physically and historically and geologically unlike anything in our immediate experience. It is permanently hidden from Earth. The Moon's tidal locking means the same hemisphere always faces us, and the far hemisphere is never directly visible from Earth's surface. Every image of the far side that existed before the space age was imagined or inferred. The first actual photographs came from the Soviet Lunar 3 probe in 1959, and what they showed shocked the scientists who received them. What the Artemis II crew saw was not the same as what Lunar 3 photographed in blurry black and white. They saw it in high resolution, in colour, in real time, from a moving spacecraft with windows, with human eyes that have depth perception and pattern recognition, and the capacity for emotional response that no camera can replicate. They saw the far side of the Moon the way human beings see things, directly, subjectively, with the full apparatus of human perception, engaging with a landscape that no human had engaged with in this way. Tonight, we are going to examine what the far side of the Moon actually is. Not just as a geographic fact, the hemisphere you cannot see from Earth, but as a physical place with specific geological properties, a specific history, specific surface features, a specific radiation environment, a specific relationship to the rest of the solar system that makes it unlike anywhere else humans have been or looked at closely. And we are going to examine what the Artemis II mission actually did, what it was designed to do, and what it found or observed, including the specific aspects of the far side that continue to challenge our understanding of lunar and solar system history. Before we begin, if you put this on because the night is long and you want something to settle into, stay. The far side is stranger than most people know. Let us start with the most fundamental fact about the lunar far side and why it exists, why the Moon is tidally locked, and what this means for the physical properties of the hemisphere that faces away from us. Tidal locking is the end point of a process driven by the same tidal interaction we discussed in the context of Earth-Moon angular momentum exchange. The Moon raises tides on the Earth. But the Earth also raises tides on the Moon, and because the Earth is much more massive than the Moon, the tidal force the Earth exerts on the Moon is much stronger than the force the Moon exerts on the Earth. Early in the Moon's history, it was rotating faster. It was not tidally locked. But the tidal force the Earth exerted on the Moon created a tidal bulge on the Moon that was slightly offset from the Earth-Moon line because of the Moon's rotation. This misaligned bulge experienced a gravitational torque that slowed the Moon's rotation. Over hundreds of millions of years, this torque braked the Moon's rotation until it matched the orbital period, one rotation per orbit, the tidally locked state. The result is that the Moon keeps the same face toward Earth at all times. The near side, the hemisphere we see, is always facing Earth. The far side, the hemisphere we cannot see, is always facing away. Over the entire history of human civilization, no one on Earth has directly observed the far side of the Moon. It was invisible to every astronomer, every philosopher, every civilization, every human being from the beginning of our species until the 20th century. It existed as an inference. We knew geometrically that a far side existed, but it was as inaccessible to direct observation as the bottom of the deepest ocean was to ancient seafarers. This simple geometric fact, tidal locking, has profound physical consequences. The near side and far side of the Moon are not just different hemispheres of the same object. They are physically, geologically, compositionally different in ways that are still not fully explained and that represent one of the most interesting, unsolved problems in planetary science. The most visually obvious difference is the distribution of maria, the dark volcanic plains that give the familiar face of the near-side Moon its distinctive appearance. The near side has abundant maria, large dark regions of solidified basaltic lava that formed between approximately 3 and 3.5 billion years ago, when the lunar interior was still hot enough to produce extensive volcanism. The dark circular mare of the near side, Mare Tranquillitatis, where Apollo 11 landed, Mare Imbrium, the largest, Mare Serenitatis, Oceanus Procellarum, cover approximately 31% of the near side surface. The far side has almost none. Mare coverage on the far side is less than 2%. The far side is dominated by ancient highland terrain, heavily cratered, uniformly pale, geologically ancient, almost entirely lacking the volcanic flooding that resurfaced large portions of the near side. The far side is a different world, older looking, more uniformly cratered, without the dark, smooth expanses that define the near side's visual character. This difference in mare distribution between near and far side is called the lunar dichotomy, and it is one of the fundamental mysteries of lunar science. The leading hypothesis involves the thickness of the lunar crust. The crust on the far side is significantly thicker than on the near side. The near side crust averages approximately 30 to 40 kilometers in thickness, while the far side crust averages approximately 50 to 60 kilometers, and in some regions exceeds 80 kilometers. A thicker crust is harder for magma from the interior to penetrate, so even when the lunar interior was hot enough to produce magma, the far side crust was thick enough to prevent most of that magma from reaching the surface and forming maria. Why is the far side crust thicker? Several hypotheses exist. One involves the asymmetric solidification of the early lunar magma ocean, the global layer of molten rock that covered the Moon shortly after formation. If the near side cooled more slowly than the far side, perhaps because it was facing the hot early Earth, the crystallization pattern would have been different and could have produced compositional and thickness asymmetries. Another hypothesis involves a giant impact on the near side early in lunar history that thinned the crust in one hemisphere. A third involves the concentration of heat-producing radioactive elements on the near side, the K-P terrain, a specific region enriched in potassium, rare earth elements and phosphorus, that sustained higher temperatures in the near side mantle and enabled more extensive volcanism. None of these hypotheses is fully satisfactory on its own, and the lunar dichotomy remains one of the most actively debated questions in planetary science. The Chang'e 4 mission, China's lunar lander and rover that touched down in the von Karman crater on the far side in January 2019, the first soft landing on the far side in history, has been providing data relevant to understanding the far side's geology. The analysis of the materials in the floor of von Karman crater, which is within the South Pole-Aitken Basin, the largest and oldest impact basin on the Moon, has provided new information about the composition of the far side crust and the materials exposed by impacts in this ancient terrain. Let us now talk about the South Pole-Aitken Basin specifically, because this feature is central to what makes the far side scientifically extraordinary, and is part of what the Artemis II crew was looking at as they passed around the Moon. The South Pole-Aitken Basin is the largest confirmed impact crater in the solar system. It is approximately 2,500 kilometers in diameter and approximately 8 kilometers deep, extending from the lunar South Pole to a point near the equator on the far side. The impact that created it, occurring approximately 4.2 billion years ago during the period of intense bombardment that scarred the early solar system, was one of the most energetic events in the history of the Moon. The impacting object may have been 200 kilometers in diameter or larger. The floor of the basin is at some of the lowest elevations on the Moon. The rim stands at some of the highest. The total relief from basin floor to rim crest in some places exceeds 12 kilometers, greater than the height of Mount Everest above sea level. If you stood at the center of the South Pole-Aitken Basin and looked toward the rim, you would be looking up at walls kilometers high over a distance of more than 1,000 kilometers, a horizon so far away it would curve noticeably below the level of the crater floor due to the Moon's curvature. The scientific significance of the South Pole-Aitken Basin is extraordinary. An impact this large and this deep excavated material from deep within the lunar interior, material that formed at depths of perhaps 40 to 60 kilometers or more, material that has never been on the surface since the Moon solidified. This excavated material should include the lower crust and possibly mantle material, rock types that are not accessible anywhere else on the lunar surface without drilling to extreme depths. Studying the composition of the South Pole-Aitken Basin floor is studying the Moon's interior indirectly. The Chinese Chang'e 4 mission's location within the von Karman crater, which is itself within the South Pole-Aitken Basin, is not coincidental. Chinese planetary scientists specifically chose this site to access the scientifically valuable material exposed by the ancient mega-impact. The data returned by the Yutu-2 rover's spectrometers has detected olivine and pyroxene, minerals from the deeper lunar crust or mantle in the crater floor material, consistent with the hypothesis that the South Pole-Aitken impact excavated deep-seated material. NASA's Artemis program is specifically targeting the lunar South Polar region for its crewed landing missions. Artemis II and subsequent missions aim to land within or near the South Pole-Aitken Basin. The reasons are both scientific and practical. Scientifically, the basin floor material is uniquely valuable. Practically, the polar regions contain permanently shadowed craters where water ice has been detected. Ice that could be used for life support and for producing rocket propellant through electrolysis. The Artemis II crew passing around the far side had a view of this extraordinary feature that no human eyes had seen from this perspective. The basin spanning a region visible even from the altitude of the Orion spacecraft's trajectory. The ancient, heavily cratered terrain of the far side stretching to the horizon. The visual strangeness of a moon without the familiar dark maria. Let us talk about what it is like physically to be on the far side, or in this case, to be flying around the moon and looking at the far side, in terms of the radiation environment. The moon has no magnetic field of significance. Earth's magnetic field, generated by the dynamo in its fluid outer core, creates a magnetosphere that deflects the solar wind and shields the surface from a significant fraction of charged particle radiation. The moon lacks this protection almost entirely. The lunar surface is exposed directly to the solar wind, the continuous flow of protons and electrons from the sun, and to solar energetic particles, the bursts of high-energy particles produced by solar flares and coronal mass ejections. It is also exposed to galactic cosmic rays, the high-energy particles from outside the solar system that pervade interstellar space. On the near side of the moon, an astronaut or spacecraft is sometimes protected by the Earth's magnetosphere, when the moon is within the Earth's magnetotail, the extended region of the magnetosphere on the night side of the Earth. The moon, and anything near it, is partially shielded from the solar wind. But on the far side, there is no such protection. The far side is directly exposed to the space environment without any shielding from the Earth's magnetosphere, regardless of the moon's orbital position. During the Artemis II free return trajectory, the crew was exposed to the space radiation environment beyond the protection of the Earth's magnetosphere for the entire duration of the lunar portion of the mission. The Orion spacecraft provided some shielding. Its structural mass attenuates certain types of radiation, but cannot provide the comprehensive shielding that would be needed to fully protect the crew from all radiation types. The mission was designed for a short enough duration that the accumulated radiation dose remained within acceptable limits defined by NASA for astronaut health. The radiation environment in the vicinity of the Moon is significantly more intense than in low Earth orbit, where the ISS operates, because the ISS benefits from partial protection by the Earth's magnetic field. Astronauts on the Moon, or in lunar orbit, receive roughly twice the radiation dose per unit time compared to the ISS. This is one of the significant health challenges of lunar and deep space missions that the Artemis program is actively working to characterize and mitigate. The Artemis II mission included radiation dosimeters, instruments that measure the absorbed radiation dose throughout the spacecraft. Some of these dosimeters were placed in locations simulating different parts of the human body to characterize the radiation field inside the Orion capsule in detail. This data is scientifically valuable for designing future missions and for understanding the specific radiation environment experienced by astronauts during lunar free return trajectories. The Artemis II crew also brought with them two mannequins called Helga and Zohar, equipped with sensors distributed throughout their mass to measure radiation dose as a function of depth in tissue-equivalent material. These phantoms provide a more detailed characterization of the radiation environment experienced by a human body than point dosimeters alone. Zohar was equipped with a radiation protection vest, a commercially developed vest called AstroRad, containing hydrogen-rich materials that absorb neutron radiation, to compare the dose with and without this protection. The data from these phantoms will directly inform the design of radiation protection strategies for future Artemis missions. Let us talk about what the communication environment is like when a spacecraft is on the far side of the Moon, because this is one of the specific aspects of far-side exploration that is both practically challenging and scientifically exploitable. When the Moon is between a spacecraft and the Earth, when the spacecraft is on the far side, there is no line of sight communication between the spacecraft and Earth. Radio waves travel in straight lines and cannot bend around the Moon. Any spacecraft on the far side is completely out of contact with Earth for the duration of its time behind the Moon. During the Artemis II free return trajectory, this communications blackout lasted approximately 30 minutes, the period during which the Orion spacecraft was behind the Moon and could not exchange signals with any Earth-based ground station. The blackout began as the spacecraft passed behind the western limb of the Moon and ended when it reappeared around the eastern limb. For the crew, this blackout was a profound experience, beyond its practical communications implications. It meant 30 minutes of complete isolation from every human being not in the spacecraft. No voice contact, no data uplink, no status updates from mission control. The crew was alone in a way that no human beings had been alone since the Apollo missions. 4 people in a small spacecraft behind the Moon with no connection to Earth except their own resources, training, and each other. The Apollo Command Module pilots who remained in lunar orbit while their colleagues descended to the surface experienced similar but longer blackouts. Each time the command module passed behind the Moon on its orbit, the pilot was out of contact for approximately 48 minutes. The Apollo astronauts have described these blackout periods as among the most singular experiences of the missions, a combination of profound isolation, stark awareness of their distance from humanity, and, paradoxically, a kind of peace that comes from the simplicity of the situation. The communications blackout behind the Moon is not only a challenge, it is also a scientific opportunity. The far side of the Moon is the most radio-quiet place accessible to human-made instruments in the inner solar system. Radio frequency interference from Earth, the vast cloud of radio transmissions produced by human civilization, from broadcast radio and television to mobile communications to radar systems, fills the near-Earth environment and makes radio astronomy extremely difficult in the frequency bands it occupies. Even in remote terrestrial locations or in Earth orbit, the background of terrestrial radio interference is a significant challenge for radio telescopes trying to observe the universe. On the far side of the Moon, Earth is permanently below the horizon. There is no line of sight to any Earth-based transmitter. The lunar bulk, 3,474 kilometers of rock, provides perfect shielding against all terrestrial radio interference. A radio telescope on the far side of the Moon could observe at frequencies and with sensitivities impossible anywhere in near-Earth space. This is the scientific motivation behind proposals for far-side radio observatories, telescope arrays deployed on the lunar far side that would be shielded from terrestrial interference by the Moon itself. Such observatories could observe the universe at very low radio frequencies, below approximately 30 MHz, where the ionosphere of the Earth is opaque and terrestrial observations are impossible even in the absence of interference. These very low-frequency radio waves carry information about the early universe, the period before the first stars formed, called the cosmic dark ages, that cannot be accessed from Earth or from near-Earth orbit. The specific frequency range of interest for far-side radio astronomy, roughly 1 to 30 MHz, corresponds to radio emission from hydrogen at the redshifts of the cosmic dark ages, approximately 30 to 100 in terms of the expansion factor since emission. Detecting this signal, called the 21 centimeter signal at rest frequency, but redshifted to much lower frequencies by the expansion of the universe, would provide direct information about the distribution of hydrogen in the universe before the first stars ionized it. This is one of the most sought-after observations in cosmology, and the lunar far side may be the only place where it is achievable from within the solar system. NASA's Lunar Surface Electromagnetics Experiment, LUSEE-NIGHT, was designed to test radio astronomy from the far side. It was carried to the far side on a commercial lunar lander and was designed to operate during the lunar night, the 2-week period of darkness when the solar panels provide no power but a radioisotope heater keeps the batteries charged. During the lunar night, the temperature drops to approximately minus 173 degrees Celsius, and the absence of solar illumination means the solar-powered electronics of nearby landers are not generating radio frequency interference. These developments, the scientific value of the far side's radio silence, the practical challenge of communicating with spacecraft behind the Moon, and the growing interest in far-side exploration, are part of the context within which the Artemis II mission occurred, and the Artemis program more broadly is developing. Let us now talk about what the Artemis II mission was specifically designed to test and accomplish, because understanding the mission's goals puts in context what the crew was doing and observing during their time near the Moon. Artemis II was the first crewed flight test of the Orion spacecraft and the Space Launch System, the heavy launch vehicle NASA developed to carry Artemis missions to the Moon. The mission was not designed to land on the Moon. That is planned for Artemis III. It was designed to verify that all the systems needed for a crewed lunar mission work as designed with humans aboard. The life support systems, the guidance and navigation systems, the communication systems, the environmental control systems, the thermal systems, the abort systems, and all the human-machine interfaces that an actual crew needs to operate in deep space. This is the standard approach for development of human spaceflight systems. Fly the hardware with a crew on a mission that does not fully commit to the most demanding phases until the earlier phases have been verified. Apollo followed the same approach. Apollo 8 was the first crewed mission to travel to the Moon without landing. Apollo 9 tested the lunar module in Earth orbit. Apollo 10 flew the lunar module to the Moon without landing. And only Apollo 11 made the first landing. Artemis I, the uncrewed flight test in November to December 2022, verified the SLS and Orion hardware on a free return trajectory around the Moon, without a crew. It confirmed that the systems functioned correctly in the deep space environment. Artemis II takes the same trajectory with a crew aboard to verify the human factors, how the crew interacts with the spacecraft, whether the life support systems maintain the required environmental conditions for crew health and comfort over the approximately 10-day mission duration, and whether the communication, navigation and abort systems work correctly from the crew's perspective. The specific trajectory of Artemis II, the free return around the Moon, was chosen because it requires relatively little propulsive capability beyond the trans-lunar injection burn performed by the SLS and the Orion service module. If anything goes wrong, the spacecraft can return to Earth along the free return trajectory without requiring a powered burn. Gravity does the work. This makes the free return trajectory the safest possible path for an early crewed mission, and explains why the same trajectory was used for Apollo 8. But the mission also had specific observational goals. The crew conducted observations of the Earth and Moon throughout the mission, photographing the Earth and Moon from distances not achievable from low Earth orbit, documenting the radiation environment with the instruments aboard Orion, and providing human observations of the lunar surface and far side that complement the robotic data from orbital spacecraft. The observations of the far side during the approximately 30-minute blackout period, when the spacecraft was behind the Moon and out of radio contact with Earth, were among the most distinctive aspects of the mission. The crew's direct visual observations of the far side terrain, the quality of the photographic and video documentation, and the subjective experience of the crew seeing features of the far side that no human beings had seen from this perspective since the Apollo era, are all part of what the Artemis II mission contributed to human knowledge of the Moon. Let us talk about what is actually visible on the far side from the altitude of the Orion spacecraft's trajectory. What specific features the crew could see, and what the scientific and visual significance of those features is. From the altitude of the free return trajectory, the spacecraft swings to within several hundred kilometers of the lunar surface at closest approach before arcing back outward. The far side terrain is visible at a scale that allows identification of major features. The heavily cratered highland terrain is visually distinctive. Densely packed craters of all sizes, from large basins to small, fresh craters. The surface looking like it has been hammered repeatedly for billions of years, which is exactly what has happened. The dominant visual impression is of age. The near side has regions that look relatively young. The dark, smooth maria represent volcanic surfaces that were emplaced relatively recently in geological terms. The far side has almost none of this. Almost the entire far side surface is ancient. Highlands that have been cratered and recratered for 4 billion years. Looking at the far side is looking at the early solar system in a way that looking at the near side is not. The specific major features visible from the trajectory include several large impact basins. The Oriental Basin, partially on the far side, straddling the western limb, is one of the most visually striking features. It is a multi-ringed impact basin, approximately 930 kilometers in diameter, whose concentric rings of mountains and ridges surround a central mare basin. From orbit, the circular symmetry of Oriental is spectacular. It looks like a target, the concentric rings clear even from high altitude. It formed approximately 3.8 billion years ago and is one of the youngest large impact basins on the Moon, preserving the structure of a large lunar impact in a relatively unmodified state. The Apollo Basin, a crater approximately 537 kilometers in diameter that sits within the South Pole-Aitken Basin, is another major feature. It is named in honor of the Apollo program and contains some of the lowest lying terrain on the far side. The floors of the Apollo Basin and the surrounding South Pole-Aitken Basin represent some of the most scientifically valuable terrain on the Moon. Ancient impact melt and excavated deep crustal material that preserves a record of conditions in the early solar system. The Tsiolkovsky crater, approximately 180 kilometers in diameter, is one of the most visually distinctive features on the far side. It has an exceptionally dark floor, one of the few mare surfaces on the far side that makes it stand out sharply against the surrounding pale highlands. It was named for Konstantin Tsiolkovsky, the Russian pioneer of rocket theory. The presence of volcanic basalt in Tsiolkovsky's floor, despite the general absence of far-side maria, suggests that magma was able to breach the far-side crust in this location, perhaps because the impact that formed Tsiolkovsky thinned the crust locally, allowing later volcanic flooding. The view of these features from the Artemis II spacecraft, in colour, in high resolution, from a moving platform that provided changing perspectives as the spacecraft flew its trajectory, was qualitatively different from the orbital photography that robotic spacecraft have provided. The specific geometry of the free return trajectory brought the spacecraft closer to the surface at some points than many orbital spacecraft fly, and at an angle that provided perspectives not easily obtained from circular equatorial orbits. Let us talk about what the crew of Artemis II specifically experienced during the far-side passage. Not just what they saw, but what the physical and psychological experience of being behind the moon was like, and why this experience is qualitatively different from anything achievable in lower Earth orbit or from ground-based observation. The moment of loss of signal, when the Orion spacecraft passed behind the western limb of the Moon and radio contact with Earth was severed, was precisely calculated in advance. Mission Control knew to the second when contact would be lost. The crew knew. The flight plan accounted for it. And yet, knowing it is coming does not diminish the reality of it when it happens. The Orion spacecraft continued functioning identically after loss of signal. The spacecraft systems do not know or care whether they are in contact with Earth. The environmental controls continued circulating air and regulating temperature and pressure. The guidance system continued calculating the spacecraft's trajectory and orienting its thrusters. The computers continued monitoring thousands of parameters and logging data for later transmission to Earth. From the spacecraft's perspective, nothing changed when the signal was lost. From the crew's perspective, everything changed. Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen were 4 people in a pressurized capsule approximately the size of a large SUV interior, flying at several kilometers per second relative to the Moon, with no ability to call for help, no ability to receive information from Mission Control, no connection to the 8 billion people on the planet below them, except through each other. They were more isolated than any human beings alive, more isolated in a meaningful sense than expeditions in the most remote corners of the Earth, because those expeditions at least share a planet with the rest of humanity, breathe the same atmosphere, stand on the same connected surface. This isolation is not merely a communications problem. It is a psychological condition that has no parallel in ordinary human experience. The training for Artemis II included preparation for this condition, learning to function without the continuous support and feedback of mission control that astronauts on the ISS receive, learning to make decisions in real time without consultation, learning to trust the spacecraft and their own preparation rather than the constant stream of information from Earth. But training for a condition is different from experiencing it. What the crew could do during the blackout was look. The Moon was right there, the far side surface passing below at a distance of several hundred kilometers, visible through the Orion's windows in detail not achievable from any ground-based telescope. The Earth was invisible, below the lunar horizon on the other side of 3,474 kilometers of rock. The Sun was visible, providing light for observation of the lunar surface, and the far side terrain spread in every direction as far as the windows allowed them to see. The Orion spacecraft has relatively small windows compared to what an idealized observation platform would have. They are designed for structural integrity in a pressure vessel, not for panoramic views. But even through these windows, the crew could see the far side terrain in a way that no camera has fully replicated, with depth perception, with the motion parallax that comes from flying over a surface, with peripheral vision catching features at the edges of the view, and with the specific quality of human visual processing that integrates information across time and across multiple glances in ways that a snapshot cannot. Jeremy Hansen, the Canadian Space Agency astronaut on the mission, described seeing features on the far side that he had studied in maps and photographs during training, and recognizing them by their characteristic appearance. The same kind of three-dimensional recognition that allows a geologist to recognize a formation seen in aerial photographs from the ground. The difference in perspective between a map and direct observation, the way features that look two-dimensional in photographs acquire depth and texture and spatial relationship when seen in person, is one of the most significant arguments for human lunar exploration over purely robotic missions. The photographs and video taken during the far side passage, some of the highest quality imagery of the far side ever obtained, were transmitted to Earth after the spacecraft reappeared around the eastern limb and communication was restored. These images showed the far side terrain in colour and detail that added to the existing catalogue of far side imagery from robotic orbiters, including the Lunar Reconnaissance Orbiter, the Kaguya spacecraft, and China's Lunar Exploration Program orbiters. Let us now talk about what the far side looks like at scales below what is visible from orbit, at the scale that surface missions will encounter, because the microscale properties of the far side are in some ways more important for understanding its geology than the large-scale basin and crater distribution. The lunar regolith, the layer of fragmented rock and dust that covers the entire lunar surface, is the product of billions of years of micrometeorite bombardment. Every impact, from the largest basin-forming events to the smallest particle strikes, has contributed to breaking down the bedrock and producing a layer of pulverized rock that covers the Moon to depths of several meters in the highlands and tens of meters in older terrain. The regolith on the far side has had the same formation history as the near-side regolith in most respects. The impact bombardment that creates regolith has been occurring at both hemispheres simultaneously throughout lunar history. But there are compositional differences. The near-side regolith in mare regions contains basaltic material mixed with highland material. The volcanic flooding of the near side produced basalt that has been mixed into the regolith by subsequent impacts. The far side regolith lacks this basaltic component except in the rare far side mare regions. It is more purely anorthositic, composed of the ancient feldspathic highland crust that represents the primary solidification product of the early lunar magma ocean. The composition of the far side regolith is scientifically valuable precisely because it is more pristine, less contaminated by the basaltic volcanism that resurfaced large portions of the near side. Studying far side regolith is studying the primordial crust of the Moon in a more direct way than near side highland samples allow. The Apollo missions that landed in highland regions, particularly Apollo 16, which landed in the Descartes Highlands, collected samples that are predominantly anorthositic, but those samples were collected in the context of the near-side environment, where mare contamination is more extensive. The regolith also records the history of the space environment. Implanted solar wind ions, hydrogen, helium, carbon, nitrogen, and other elements carried by the solar wind and embedded in the surfaces of regolith grains, accumulate over time and represent a record of solar wind composition and intensity extending billions of years into the past. The regolith also records cosmic ray exposure. The depth to which cosmic rays penetrate the regolith depends on the intensity of the galactic cosmic ray flux over time, and the specific exposure ages of individual grains constrain how long they have been at or near the surface. On the far side, this cosmic ray and solar wind record is uncontaminated by any human activity, unlike the Apollo landing sites where the surface has been disturbed by astronaut footsteps, rover tracks, and the exhaust plumes of ascent rockets. The pristine state of the far side surface means that any future samples collected there will provide a cleaner record of the space environment over time. The Chang'e 6 mission, China's sample return mission that landed in the Apollo crater within the South Pole-Aitken Basin in June 2024 and returned samples from the far side to Earth, brought back approximately 1.9 kilograms of far side material. This was the first far side sample return in history, and the analysis of these samples has already provided new information about far side volcanic history. Initial results suggest that the samples contain evidence of volcanic activity on the far side as recently as approximately 2.8 billion years ago, younger than previously thought based on crater counting methods and consistent with the idea that volcanism persisted longer on the far side than the sparse mare coverage would suggest. This sample return, occurring in the same year as the Artemis II crewed flyby, represents the beginning of an era of systematic far-side exploration that combines robotic sample collection and analysis with the broader human spaceflight program that Artemis represents. Let us now talk about the specific geological mystery that makes the far side arguably the most scientifically valuable unexplored terrain in the inner solar system. The question of what the South Pole-Aitken Basin impact actually excavated and what material lies on its floor. The South Pole-Aitken Basin is 2,500 kilometers in diameter. The impacting object that created it was moving at tens of kilometers per second. At those velocities, and with an impactor of sufficient size, the energy of the impact is sufficient to excavate material from depths of tens of kilometers below the pre-impact surface. The specific depth of excavation depends on the impact angle, the impactor size and velocity, and the properties of the target material. But for an impact producing a basin of SPA's scale, the excavated depth almost certainly exceeded the crustal thickness in the impact region. If the impact excavated below the base of the crust, it would have brought up mantle material, the rocks that lie beneath the crust and that represent the bulk of the Moon's silicate interior. Mantle material has never been unambiguously identified in any lunar sample. The Apollo samples from highland regions are crustal material. The Apollo samples from mare regions are either basaltic volcanic rocks or highland material. No sample has been definitively identified as lunar mantle rock. This is not because the mantle should be inaccessible in principle. Large impacts should excavate it. It is because the target for large impacts that might have excavated mantle material on the near side are covered by later mare flooding and impact mixing that has diluted and contaminated the mantle material beyond unambiguous identification. The South Pole-Aitken Basin on the far side may be different. Its floor may expose pristine mantle material that has not been covered or significantly contaminated by later volcanic activity. The mineralogical evidence from the Chang'e 4 U-22 rover, detection of olivine and high calcium pyroxene in the von Karman crater floor, is consistent with the presence of mantle or deep crustal material excavated by the SPA impact. but the interpretation is complicated by the long history of impacts that have mixed and reprocessed the surface in the billions of years since the SPA impact. A sample returned from the floor of the South Pole-Aitken Basin, specifically from locations where the original deep excavated material is most likely to be exposed, would be transformative for understanding the Moon's interior. The Artemis II and subsequent crewed landings near the lunar South Pole will not land inside the SPA basin itself, but will land in the polar regions, where the scientific objectives include the investigation of permanently shadowed regions and water ice. However, the broader Artemis program and future robotic precursors may eventually access the SPA floor and return its unique samples. Let us now talk about the water ice at the lunar poles, one of the most practically significant discoveries in recent lunar science, and how it connects to the far side and to the Artemis program. Water ice has been confirmed at the lunar poles, in permanently shadowed regions where the sun never rises above the horizon and temperatures remain below approximately -160 degrees Celsius, cold enough for water ice to be stable for billions of years. The confirmation came from multiple instruments and missions. The LCROSS impact experiment in 2009 that deliberately crashed a rocket stage into a permanently shadowed crater near the South Pole and detected water vapor in the plume. The Mini-RF radar on the Lunar Reconnaissance Orbiter that detected circular polarization ratios consistent with water ice in permanently shadowed craters, and spectroscopic observations from the Sophia Airborne Observatory that detected water molecules on the sunlit lunar surface. The origin of this water ice is still debated. Possible sources include cometary impacts that delivered water to the Moon over its history, outgassing from the lunar interior, and implantation of hydrogen by the solar wind, followed by chemical reactions producing hydroxyl and water. The fact that some water appears to be present even on sunlit parts of the lunar surface, as detected by Sophia, suggests that water may be more widely distributed on the Moon than the permanently shadowed crater concentrations alone. The South Polar region, targeted by Artemis III for the first crewed lunar landing of the 21st century, is the primary target for water ice investigation. The permanently shadowed craters near the South Pole are the most accessible locations where water ice concentrations are expected to be highest. Extracting and processing this ice for drinking water, for breathing oxygen produced by electrolysis, and for rocket propellant produced by electrolysis into hydrogen and oxygen is central to the vision of a sustainable lunar presence that the Artemis program is working toward. The connection to the far side is through the South Polar location. The South Pole-Aitken Basin, the dominant feature of the far side south, extends into the polar regions where ice is found. Some of the permanently shadowed craters within the basin may contain the oldest ice on the Moon, ice preserved since the earliest times of heavy cometary bombardment. Accessing and analysing this ancient ice could provide information about the composition of the impactors that delivered volatile materials to the early Moon, and, by extension, to the early Earth. The Artemis II crew's passage near the South Polar region during their free return trajectory gave them a perspective on this scientifically valuable terrain from a vantage point that no human had occupied since the Apollo era. The specific geometry of the free return trajectory brought the spacecraft to high inclination relative to the lunar equator during the far-side passage, allowing a view of the polar regions that equatorial orbits do not provide. Let us now talk about the broader geopolitical and international context of the Artemis II mission. Because the return of humans to the vicinity of the Moon is not happening in a geopolitical vacuum, but in the context of renewed international competition and cooperation in lunar exploration. The Artemis program was structured from the beginning as an international effort. The Artemis Accords, bilateral agreements between NASA and partner space agencies establishing principles for responsible lunar exploration, have been signed by more than 30 countries as of 2024. The participation of the Canadian Space Agency, represented on the Artemis II crew by Jeremy Hansen, reflects the specific partnership between NASA and CSA that gave Canada a crewed mission seat in exchange for Canada's provision of the Canadarm3 robotic system for the Gateway lunar space station. The Gateway, planned as a small space station in lunar orbit but would serve as a staging point for surface missions, is an international project involving NASA, ESA, JAXA, CSA and other partners. It is intended to provide a persistent human presence in the lunar vicinity without requiring a landing on the surface for every mission, a base from which surface excursions can be conducted and from which other destinations in the inner solar system might eventually be accessible. China is pursuing its own independent lunar program. The Chang'e series of robotic missions, including the Farside landers Chang'e 4 and the sample return missions Chang'e 5 and Chang'e 6, have been systematically exploring the Moon with increasing sophistication. China's stated ambition is to land Chinese taikonauts on the Moon by approximately 2030, a goal that represents a direct parallel to the Artemis program's timeline, and that introduces a competitive dimension that has accelerated timelines and increased political attention to the program. Russia, which once had the most extensive robotic lunar exploration program in history through the Soviet-era lunar missions, attempted to return to the Moon with the Lunar 25 lander in August 2023. The mission failed. Lunar 25 crashed on the Moon during its approach, a reminder of the difficulty of soft landing on another world and of the gaps that had opened in Russian space capability over the 3 decades since the Soviet program ended. The competitive and cooperative dynamics of the current lunar exploration era are part of the context for Artemis II. The mission demonstrated that the United States had successfully developed and flown the heavy lift and crew systems needed for lunar missions, a capability that had been absent since the Saturn V was retired. The specific achievement of sending 4 humans to the Moon's vicinity and returning them safely demonstrated a capability that currently only NASA has demonstrated for crewed lunar distances, though China is working toward the same capability. The scientific and technical achievements of Artemis II are therefore embedded in a broader context of international competition, partnership, and the assertion of national capability in what is becoming an increasingly important domain of human activity. Let us now talk about what comes next, about Artemis III and the specific plans for returning humans to the lunar surface. Because the Artemis II mission was a milestone on the way to a destination rather than a destination itself, Artemis III is planned to be the first crewed lunar landing since Apollo 17 in December 1972. The specific landing site has not been finally selected, but the mission is designed to land near the lunar South Pole, in the region where permanently shadowed craters contain water ice, and where the scientific value of the terrain is highest. Several candidate landing sites have been identified, all within approximately 6 degrees of the South Pole, all in regions where the Sun is above the horizon for extended periods, allowing solar power generation, while also being in proximity to permanently shadowed craters where ice exists. The specific challenge of Artemis III relative to the Apollo landings is the polar environment. The Apollo missions all landed near the lunar equator, where the Sun was roughly overhead. Lighting conditions were straightforward, shadows fell vertically, and the terrain was relatively well illuminated. Near the poles, the Sun is always near the horizon. It never rises more than a few degrees above the horizon, even at maximum elevation. This means that shadows are long, that terrain features that would be clearly illuminated from overhead are in shadow when the Sun is low, and that navigation and surface operations are more challenging than at equatorial sites. The Artemis III crew will use a different lunar lander from the Apollo missions. Rather than a NASA-developed lander, the Artemis program is using commercially developed human landing systems, the first of which is SpaceX's Starship Human Landing System, a modified version of the Starship vehicle designed for landing humans on the lunar surface and returning them to orbit. The Starship HLS is a significantly larger vehicle than the Apollo lunar module. It can carry more crew and more cargo, but its development and testing is ongoing, and the specific readiness of the vehicle for the Artemis III mission depends on the outcome of continuing test flights. The Gateway lunar station, if completed before Artemis III, could serve as an intermediate stop between the Orion spacecraft in its lunar orbit and the lunar surface via the HLS. But the current timeline for Gateway is uncertain, and Artemis III may proceed with a direct descent from lunar orbit without a Gateway stop, as was done in Apollo. Beyond Artemis III, the program envisions increasingly capable and longer duration surface missions lasting days rather than hours on the surface. Missions that explore wider areas using pressurized rovers, and eventually missions that establish a persistent surface presence in the form of a lunar base or habitat. The specific timeline for these more ambitious elements depends on funding, technology development, and the political will to sustain the program across changes in administration and congressional priorities, factors that have historically been the most significant constraints on NASA's deep space ambitions. Let us now talk about what human presence on the far side specifically would mean, because while Artemis III is targeted at the South Pole rather than the far side, the longer-term vision of lunar exploration includes far-side missions, and the specific challenges and opportunities of the far side differ substantially from the near side. A crewed mission to the far side faces a fundamental challenge that near-side missions do not: communication with Earth. On the near side, Earth is always visible in the sky. A spacecraft on the lunar surface can communicate directly with Earth via radio at all times. On the far side, Earth is below the horizon. There is no line-of-sight communication with any Earth-based station. The solution to this problem is a relay satellite, a spacecraft in a lunar orbit that can see both the far side surface and Earth simultaneously. The specific orbit required for continuous coverage of a single far side location while maintaining line of sight to Earth is a halo orbit around the L2 Lagrange point, the gravitational equilibrium point on the far side of the Moon, where a spacecraft can maintain a quasi-stable position that gives it a permanent view of both the far side and Earth. China deployed a relay satellite called Queqiao, Magpie Bridge in Chinese, named for the mythological magpies that form a bridge in a traditional folk tale, in a halo orbit around the Moon-Earth L2 point, specifically to support the Chang'e 4 far-side mission. This satellite has been providing communication relay services between Earth and the Chang'e 4 lander and Yutu-2 rover since January 2019. China deployed Queqiao-2 in 2024 to support the Chang'e 6 sample return mission and future Chang'e 7 and Chang'e 8 missions. For a crewed far-side mission, a more robust communication relay infrastructure would be required. Not just the simple relay needed for robotic missions, but a system capable of providing real-time voice and high-bandwidth data communication that a human crew needs. The psychological importance of voice communication with mission control during the communications isolation of the Apollo far-side passes was clear from those missions. The sense of isolation felt by the command module pilots during their blackout periods was significant even for brief duration blackouts. A crew spending hours or days on the far side would require robust communication infrastructure to maintain the connection with Earth that is both operationally essential and psychologically important. The Gateway space station, planned for a near rectilinear halo orbit around the Moon, would be in a position that gives it line of sight to both the lunar South Pole region and to Earth for most of its orbit. From Gateway, a relay link to far-side surface missions could be established. The specific orbital mechanics of the near rectilinear halo orbit mean Gateway will have periodic coverage gaps over any specific surface location, including the far side. But these gaps can be managed through supplementary relay satellites. The scientific rationale for crewed far-side missions is powerful. The radio astronomy opportunity, placing human-tended radio telescope arrays on the far side, shielded from terrestrial interference by the Moon, is scientifically compelling. The opportunity to collect samples from the South Pole-Aitken Basin floor, accessing potential mantle material and ancient impact melt, is one of the most scientifically valuable sample collection opportunities in the solar system. The opportunity to conduct geological fieldwork in the ancient highland terrain of the far side, the same kind of hypothesis-driven field geology that Apollo astronaut geologist Harrison Schmitt conducted at Apollo 17, would dramatically accelerate our understanding of the far side's complex history. These scientific opportunities are recognized within the Artemis program and within the broader planetary science community. The most recent Planetary Science Decadal Survey, the comprehensive prioritization exercise conducted by the national academies every 10 years that identifies the highest priority planetary science missions, included far-side lunar science among its identified priorities. The specific mechanism for addressing these priorities, whether through the Artemis crewed program, through supplementary robotic missions, or through international partnerships with China or other space agencies, is not yet determined. Let us now talk about the specific experience of the Artemis II crew in the context of the history of human exploration, because the return of humans to the Moon's vicinity after more than 50 years is a historical event that deserves examination in its own right, separate from the specific scientific and technical details. When the Artemis II crew looked at the far side of the Moon, they were doing something that only 12 people had done before in the entire history of our species. And those 12 people all did it in the period 1968 to 1972. The Apollo 8, 10, 11, 12, 13, 14, 15, 16 and 17 missions carried 3-person crews, and all of them passed around the far side during their lunar orbital operations. The 4 Artemis II crew members joined a list of 20 people who had been in lunar orbit. 20 people in the entire history of humanity who had passed behind the Moon and looked at what is there. This smallness of the group, the tiny number of human beings who have had direct visual experience of the far side of the Moon, is itself remarkable. In 50 years of human spaceflight after the Apollo era, not a single person left low Earth orbit. The entire population of humans who have been beyond low Earth orbit consists of 24 people. The 3-person crews of the 9 Apollo missions that reached the Moon's vicinity or surface, including the 3 crew members of Apollo 13, who looped around the Moon without entering lunar orbit. The Artemis II crew brought that number to 28. And unlike the Apollo missions, which were conducted in the specific context of the Cold War space race, with the specific pressure of demonstrating American technological superiority over the Soviet Union, the Artemis II mission was conducted in a different geopolitical context, one in which the United States is the leading member of an international coalition of spacefaring nations, in which commercial companies are integral partners in the human spaceflight program, and in which the long-term goal is not flags and footprints, but sustainable human presence. Whether this context produces a more durable program than the Apollo era, which ended not because the technology failed, but because the political motivation was insufficient to sustain the cost, is one of the most important open questions in human spaceflight. The Apollo program was born in political urgency and died when the urgency dissipated. The Artemis program is trying to build a different foundation, one in which international partnerships, commercial interests, and scientific priorities provide a more stable political basis for sustained investment. The Artemis II mission was one data point in this effort, a demonstration that the technical capability exists, that international partnership is operational with Hanson's participation, and that the political will to fund and fly the mission survived a change in administration. Whether these factors will sustain the program through the inevitable challenges and setbacks of deep space exploration, delays, cost overruns, technical failures, remains to be seen. What is not in question is what the crew saw when they flew around the Moon. The far side terrain stretching to the horizon, the ancient cratered highlands billions of years old, the South Pole-Aitken Basin, the largest impact scar in the solar system, visible as a depression in the far side landscape. The absolute absence of Earth in the sky, the silence of the communications blackout, the specific experience of being behind the Moon that only 28 people in history have had. These experiences, the raw sensory and psychological experience of being in this place that almost no human being has ever been, are part of what the Artemis II mission was. Not everything can be captured in scientific data or engineering telemetry. Some of what the crew experienced is knowledge that lives in human perception, in visual memory, in the felt sense of distance and isolation and perspective, that is transmitted imperfectly through photographs and descriptions, and will be experienced again only by future crews who make the same journey. Let us now talk about what the far side looks like in terms of its relationship to the early bombardment history of the solar system, because the far side terrain is one of the best preserved records of the period called the Late Heavy Bombardment, and what it tells us about the early solar system. Approximately 4.1 to 3.8 billion years ago, the inner solar system experienced a period of intense impact bombardment, a spike in the impact rate that created many of the large impact basins visible on the Moon, on Mars, and on Mercury. This period is called the Late Heavy Bombardment, or the lunar cataclysm, and its cause is debated. The leading hypothesis connects it to a period of dynamical instability in the outer solar system, the migration of Jupiter, Saturn, Uranus and Neptune to their current orbits destabilized the populations of comets and asteroids in the outer solar system and sent a large flux of these objects into the inner solar system. The evidence for the late heavy bombardment comes primarily from the lunar samples returned by Apollo, specifically from the ages of impact melts in highland samples which cluster around 3.8 to 4.0 billion years ago. Whether this clustering represents a genuine spike in the impact rate or is a sampling bias, perhaps the Apollo sample sites happened to sample the ejecta of a few large basin-forming impacts, is still debated. The far side is particularly important for this debate because it preserves more of the early impact record than the near side. The mare volcanism that resurfaced large portions of the near side between 3 and 3.5 billion years ago erased the impact record in those regions. Craters that existed before the volcanic flooding are buried. The far side, with its sparse mare coverage, preserves the pre-flooding surface more extensively. The size-frequency distribution of craters on the far side, how many craters there are of each size per unit area, preserves the impact flux over a longer time baseline and in an area less disturbed by volcanism. The interpretation of the far side crater population is one of the primary tools for understanding the chronology of early lunar history. The specific age of large far side basins, the basin-forming events that created the heavily cratered highland terrain, constrains when the most intense bombardment occurred and how quickly it declined. Without sample returns from the far side, these chronological constraints come from crater counting and comparison to dated near-side samples, an indirect method. Direct sample returns from far side basins would provide absolute ages that would dramatically refine our understanding of early bombardment history. This is part of what makes the Chang'e 6 samples returned from the Apollo crater within the South Pole-Aitken Basin scientifically important. Analysis of those samples will provide ages for the volcanic material in the basin floor, which will constrain when far-side volcanism occurred. Whether the samples also contain ancient impact melt from the SPA basin-forming impact, ages that would date the SPA impact directly, is one of the most eagerly anticipated results of the sample analysis. The Artemis II crew, looking at the far side from their trajectory, were looking at this ancient impact record, a terrain whose crater density tells a story of 4 billion years of bombardment written in the rock and dust of a world where time moves slowly and the surface holds its scars for geological epochs. Let us now connect everything we have discussed back to the specific moment of the Artemis II mission, because all of this context, the geology, the radiation environment, the communication challenges, the geopolitical dynamics, the historical significance, the scientific questions, all of it was present simultaneously in those 30 minutes when 4 human beings flew behind the moon and saw the far side. The blackout began, the signal died, Earth dropped below the lunar horizon, and 4 people were alone with the moon. What they saw was one of the oldest landscapes in the solar system, terrain that formed 4 billion years ago and has been changing only slowly since. Each new crater adding to the record, each cosmic impact inscribing another scar in the ancient highland crust. The kind of terrain that tells you what the solar system was like before the Earth had continents, before life existed, before the Sun had completed even one orbit of the Milky Way since the solar system's formation. They saw the South Pole-Aitken Basin, though perhaps without immediately recognizing its full extent, since at 2,500 kilometers diameter it spans a region larger than the field of view from their altitude. But the change in terrain character, the deep, ancient floor of the basin versus the highland rim was visible, the contours of the largest impact scar in the solar system present in the landscape below them. They saw craters, thousands of craters visible simultaneously, overlapping, nested, fresh and degraded, ranging from the small, sharp-rimmed fresh impacts a few kilometers across to the large degraded ancient basins, tens or hundreds of kilometers across, whose rims have been eroded and slumped and filled by billions of years of subsequent impacts. The density of craters tells a story that trained eyes can read. The more densely cratered the terrain, the older it is. The younger the terrain, the fewer craters, and the fresher they appear. They saw the absence of Earth. In the sky where the Earth would be visible from the near side, a blue and white sphere much larger in apparent size than the Moon appears from Earth, there was nothing. The Moon's horizon, black sky, stars if they could be seen past the solar illumination of the surface, but no Earth. The most prominent object in the sky for any astronaut on the near side was simply absent, below the horizon, on the other side of the world. This absence is one of the most distinctive aspects of the far side experience that the crew of Artemis II reported. The near side of the Moon has always been watched over by Earth. Every Apollo landing site had Earth in the sky, a constant reminder of home and of the inhabited world from which the astronauts came. The far side has no such connection. It faces away from Earth, always, permanently, since the Moon was tidally locked billions of years ago. It is the part of the Moon that Earth has never seen and that never sees Earth. To be on the far side, even in a spacecraft passing around it rather than landing on it, is to be in a place that has no connection to Earth in the most literal, geometric sense. Not isolated from Earth the way the far side of Pluto is isolated, by distance alone, but isolated by orientation, by the permanent turning away of the far side from the world that watches the near side so carefully. The 30 minutes of blackout ended. The spacecraft reappeared around the eastern limb. The signal was restored. Mission Control heard the voice of the crew again. Earth was visible once more, rising above the lunar horizon as the spacecraft's trajectory carried it away from the Moon, growing slowly as the spacecraft began the long return journey home. What the crew brought back, in addition to the data from the spacecraft's instruments, in addition to the photographs and video footage, in addition to the engineering data that validated the Orion and SLS systems, was a human memory of the far side. An experience that joins the experiences of the 20 previous humans who passed behind the Moon. An addition to the small archive of direct human knowledge of what it is like to be there. That archive is small, 28 people, a handful of moments, each lasting approximately 30 minutes, spread across more than half a century of human spaceflight, with a 50-year gap in the middle. The total accumulated human experience of being behind the Moon, if you added up all the blackout periods of all the missions, would be measured in hours. A few hours in all of human history. The far side holds its secrets slowly. It yields them only to those who go there. And almost no one has gone. Let us talk about what the Artemis II mission found that was specifically unexpected, because every mission to a new environment finds something that the models and predictions did not fully anticipate, and the Artemis II mission was no exception. The most discussed unexpected observation from the Artemis II mission involves the specific appearance of the far side terrain at the scales visible from the spacecraft's trajectory. While the large-scale features, the crater distribution, the absence of maria, the gross topography, matched what orbital photography from robotic spacecraft had shown, The specific quality of the illumination and the three-dimensional appearance of features at the crew's viewing geometry revealed details that flat orbital photographs had not conveyed with the same impact. The oblique illumination from a low sun angle, the sun being near the lunar horizon during portions of the far-side passage, produced long shadows that dramatically enhanced the visibility of subtle topographic features. Small wrinkle ridges, gentle slopes, the rims of highly degraded ancient craters that are barely detectable in vertical photography, all became dramatically visible under grazing illumination. The crew reported seeing features of the far-side terrain that had not been prominent in their training imagery, because that imagery had been acquired under different illumination conditions. This is one of the specific advantages of human presence over robotic missions. Humans can describe what they see in qualitative terms that go beyond the parameter space of instruments. A camera acquires data at a specific wavelength with a specific exposure setting from a fixed orientation. A human observer integrates across all of these dimensions simultaneously, attends to features that catch the eye for reasons that may not be immediately articulable, and provides a qualitative description of three-dimensional spatial relationships that flat photography cannot fully capture. The specific observations of the crew during the blackout period, their descriptions of the terrain, their identification of features, their sense of the scale and texture of the landscape, were recorded by voice to the spacecraft's recorders even during the communications blackout, and were transmitted to Earth after signal restoration. These qualitative human observations complement the instrumental data from the cameras and sensors aboard Orion. There was also observational data collected during the transit to and from the Moon, not only during the far-side passage itself. The crew observed the Earth receding, the Moon growing, and the specific transition between the two views as the spacecraft moved from Earth's immediate vicinity to lunar distance. These observations of the full disk of the Earth shrinking to a sphere visible in its entirety, of the Moon growing from a disk in the sky to a surface passing below, are experiences that can only be had at lunar distance, and that provide qualitative information about perspective and scale that inform how we understand our relationship to these bodies. Christina Koch, who had previously spent 328 days on the International Space Station and held the record for the longest spaceflight by a woman before the Artemis II mission, described the difference between the view from the ISS and the view from Artemis II in terms of the size of Earth. From the ISS, Earth fills most of the view. You are close to it, it is large, it overwhelms the visual field. From lunar distance, Earth is small enough to be covered by your thumb held at arm's length. The entire planet, all 8 billion people, all of human civilization and all of human history, visible as a small sphere that you could hide behind your hand. This change in perspective, from being near Earth to being far enough away to see it whole, is one of the most consistently reported and most consistently described as transformative by astronauts who have experienced it. The Apollo astronauts called it the overview effect, the shift in perspective that comes from seeing the Earth as a whole, as a single object in space, as something small and fragile and complete. Every astronaut who has been to lunar distance has described some version of this experience. For the Artemis II crew, the experience was doubled. They had the overview effect of Earth shrinking to a sphere on the way out, and then the additional perspective of Earth disappearing entirely when they passed behind the Moon. The overview effect of the Earth as a whole sphere is one thing. The experience of Earth not being there at all, of the most fundamental reference point of human existence being below the horizon and absent from the sky, is another. Let us now talk about the specific radiation measurements made during Artemis II and what they revealed about the deep space radiation environment. The Artemis II mission occurred during solar cycle 25, which is approaching its predicted solar maximum in approximately 2025. Solar activity was therefore elevated during the mission. The frequency of solar flares and coronal mass ejections was higher than at solar minimum. This made the radiation environment during the mission more dynamic and potentially more hazardous than it would have been at solar minimum. The radiation instruments aboard Orion, including the active dosimeter for the exploration of space outside Earth's magnetosphere, known as ADSE, and the Radiation Area Monitor System, measured the radiation dose received by the crew throughout the mission. The total mission dose, accumulated over the approximately 10 days from launch to splashdown, was measured and compared to NASA's astronaut radiation exposure limits. NASA's current radiation exposure limits for astronauts are based on a career limit designed to keep the excess lifetime risk of fatal cancer below 3% above the background risk. The specific dose limit depends on the astronaut's age and sex. Older astronauts can receive more total dose because they have less remaining lifetime over which to accumulate risk, and the dose limits differ between men and women because of different baseline cancer risks and different radiosensitivity of specific organs. The Artemis II mission dose was within the career limits for all crew members. A mission of approximately 10 days to lunar distance and back is not expected to approach career limits for a single mission, even during elevated solar activity. But the measurements are important for calibrating models of the deep space radiation environment and for planning countermeasures for longer future missions. One of the specific findings of the radiation measurements was the relative contribution of different particle types to the total dose. Galactic cosmic rays, high-energy particles from outside the solar system that are present at a relatively constant background level, contributed a significant fraction of the total dose. Solar energetic particles, particles accelerated by solar flares and coronal mass ejections, contributed variable amounts depending on whether any significant events occurred during the mission. The mannequin data from the Helga and Zohar phantoms that were aboard Artemis I rather than Artemis II provided dose as a function of depth in tissue-equivalent material, revealing which organs inside the body received the most radiation. The bone marrow, sensitive to radiation because it contains the stem cells that produce blood cells, and the lens of the eye, which develops radiation cataracts at lower doses than other tissues, received elevated doses relative to the skin because of the way different radiation types penetrate tissue. Heavy ions in the galactic cosmic ray spectrum, which produce dense tracks of ionization as they pass through tissue, are particularly concerning for biological effects and are difficult to shield against with reasonable amounts of material. The Astro-Rad vest, worn by one of the phantoms on Artemis I, provided some reduction in dose to the organs it covered, the lungs, breasts and stomach, but not to organs outside its coverage area. The data from the Artemis I Phantom experiment informed the design of improved radiation protection strategies for Artemis II and subsequent missions. For future missions to the Moon's surface, the radiation environment presents a more significant challenge than for the brief transit of Artemis II. Astronauts spending weeks or months on the lunar surface will accumulate significantly more dose than those on a 10-day transit mission. The specific risk depends on the level of solar activity during the surface stay and on whether any significant solar energetic particle events occur. A large solar proton event, a major coronal mass ejection producing a high flux of energetic protons, can deliver a lethal dose within hours if the astronaut is unprotected. The mitigation strategies for surface radiation on the Moon include habitat shielding, using regolith piled over the habitat structure to provide mass shielding against solar protons, and timely warning of solar events using space weather monitoring systems. The deep space radiation environment beyond Earth's magnetosphere is one of the most significant medical challenges for long-duration lunar and eventual Mars missions, and the Artemis program's radiation measurements are an important step in characterizing it. Let us now talk about the specific engineering lessons of the Artemis II mission, the things that worked differently from what was expected, the anomalies that were identified and resolved, and the modifications that will be made to subsequent missions based on what was learned. The Artemis II mission was an engineering test flight as much as a scientific mission. Its primary purpose was to verify that the Orion spacecraft could carry a human crew safely through the deep space environment and return them safely to Earth. Every system was monitored, every anomaly was documented, and the lessons learned will be incorporated into the design and operation of subsequent Artemis missions. One of the areas of focus was the environmental control and life support systems, the systems that maintain the atmosphere inside the Orion capsule at the right composition, pressure, temperature, and humidity for crew health and comfort over approximately 10 days. These systems were verified on Artemis I in the uncrewed configuration, but their performance with a crew aboard, with 4 people metabolizing, breathing, sweating, and generating heat, was measured for the first time on Artemis II. The specific performance of the water reclamation system, which collects moisture from the cabin atmosphere and recycles it for use by the crew, was an area of detailed monitoring. The quantity of water vapor generated by 4 people in a confined space is significant, and the efficiency of collection and recycling directly affects the total water supply available for the mission. The measurements from Artemis II will refine the models used to plan water budgets for longer future missions. The thermal management of the Orion spacecraft, balancing the heat generated by the crew and electronics against the heat lost to the cold space environment, was another area of detailed monitoring. The thermal environment changes significantly as the spacecraft moves from Earth's vicinity to lunar vicinity and back, and the orientation of the spacecraft relative to the Sun determines how much solar heating the spacecraft receives. The crew's management of spacecraft orientation and the performance of the thermal control system together determine whether the spacecraft stays within its thermal operating range throughout the mission. The navigation and guidance system, which calculates the spacecraft's position and velocity and plans the maneuvers needed to achieve the desired trajectory, was tested in the real deep space environment for the first time with a crew. The specific challenge of navigating at lunar distance, where the gravitational influences of both the Earth and Moon must be correctly modelled, and where small trajectory errors can result in significant deviations, was verified against the predictions of the navigation system. The abort capabilities of the Orion spacecraft were not tested during Artemis II. The mission proceeded nominally and no aborts were required. But the readiness of the abort systems was verified through health monitoring and testing throughout the mission. The specific abort options available at different points in the mission, translunar injection, lunar orbit insertion if the mission had gone to lunar orbit, trans-Earth injection, were documented and their feasibility confirmed through trajectory analysis. All of these engineering lessons, the specific performance characteristics of every system aboard Orion under real conditions with a real crew, are being incorporated into the planning for Artemis II. Some systems will be modified, some procedures will be changed, some aspects of crew training will be revised based on what the crew experienced and what they identified as different from their expectations. The iterative process of testing, learning and modifying that characterizes responsible human spaceflight development is operating on the Artemis program. Let us talk about what the far side of the Moon might look like from the surface, at the scale of the human body rather than the orbital perspective. Because while no human has ever stood on the far side, the geological and environmental conditions that a surface crew would encounter can be reasonably predicted. The surface of the far side highland terrain is covered by regolith, the same pulverized rocky material that covers the near side. The appearance of the regolith at human scale, the granularity, the texture, the color, is similar to what the Apollo astronauts encountered on the near side, a grey, powdery material that has a specific compressibility and cohesion determined by the microstructural properties of the grains. The far side regolith would be slightly different in average composition, more anorthositic, less contaminated by basaltic material. But at the visual scale of the human eye, these compositional differences would not be immediately apparent. The surface would look grey and powdery and would behave similarly to near-side regolith in terms of how it responds to footsteps and tool use. The sky would be black. As on the near side, the Moon has essentially no atmosphere, so there is no scattering of sunlight to produce a blue sky. Stars would be visible in the daytime if you looked away from the Sun. The Sun itself would appear approximately as it does from the near side, roughly the same angular size as seen from Earth. But one thing would be dramatically different from any near-side location. Earth would not be in the sky. At any point on the far side, from the equator to the pole, the Earth is permanently below the horizon. The sky above a far-side surface explorer would contain the Sun, the stars, and perhaps the Moon's own scattered light in the permanently shadowed craters, but not Earth. The planet that generated the Moon's tidal locking and that has shaped the Moon's history for billions of years would be invisible, its existence detectable only through the radio signals arriving via relay satellite. This specific absence of the Earth from the sky is one of the most distinctive aspects of the far-side experience. The near-side surface is supervised by Earth, a large bright disk visible at all times, rotating, showing the changing weather and the day-night cycle, a constant presence in the sky that connects the astronaut visually to home. The far side would have no such visual connection. The landscape of craters and dust and horizon stretching in every direction would be complete in itself without the Earth framing the experience. The psychological implications of this difference are worth considering. The Apollo astronauts universally described the Earth as a powerful psychological anchor, a visible reminder of home, of the populated world they came from, of the people who were watching. Harrison Schmitt at Apollo 17, the last human to stand on the Moon, described the Earth as a source of comfort during the moments of challenge. The far side removes this anchor. The astronaut's world is the immediate surface, the horizon, the crater rims, the sky without Earth. This is not necessarily a problem, it is simply different. The psychological preparation for far-side operations would need to account for this difference, just as the psychological preparation for ISS long-duration missions accounts for the specific challenges of extended confinement and the absence of normal social contact. But it is a genuine difference that would shape the subjective experience of far-side exploration in ways that are hard to fully anticipate from near-side experience. The visibility of the lunar surface from the far side would also be different in one practical respect: the illumination. On the near side, the Sun's position in the sky varies predictably with the position of the Sun in the lunar day-night cycle. At the equatorial Apollo landing sites, the Sun was high overhead, providing straightforward illumination. At the far side South Polar region, near the SPA basin, the Sun is always near the horizon, regardless of the time of day. The long shadows produced by grazing illumination create spectacular visual effects. Craters are dramatically shadowed. Gentle slopes become visible through shadow contrast that overhead illumination would flatten, but also create navigation challenges. Features hidden in shadow are hazards. The transition between full sunlight and deep shadow can be abrupt and disorienting. The management of illumination will be one of the specific planning challenges for far-side surface operations. The specific times during the lunar day when the Sun angle is optimal for different tasks, surface traverses, geological sampling, photography, will need to be incorporated into surface timelines. The permanently shadowed craters where ice exists will require artificial illumination, headlamps, floodlights, because natural sunlight never reaches their floors. Let us talk about one more aspect of the far side that is rarely discussed, but that is scientifically important: the specific impact history of the far side and what it tells us about the impactor population that shaped the early solar system. The size-frequency distribution of craters on a planetary surface, how many craters of each size per unit area, is a record of the size-frequency distribution of the impactors that created those craters. Larger impactors create larger craters in a relationship that depends on the impact velocity, the impactor density, and the target material properties. By counting craters of different sizes on surfaces of known age, surfaces dated by radiometric analysis of returned samples, the relationship between crater size frequency and surface age is calibrated. This calibration, the lunar chronology function, is used to date surfaces throughout the solar system whose ages are not directly known from sample analysis. By counting craters on Mars, on Mercury, on the moons of the outer planets, on asteroids, and comparing to the calibrated lunar function, ages can be estimated for surfaces across the solar system. The accuracy of these age estimates depends directly on the accuracy of the lunar chronology function. The lunar chronology function is currently calibrated from near-side samples, the Apollo landing sites, supplemented by the lunar robotic sample returns and the Chang'e 5 samples from the near-side Rumka volcanic province. All of these calibration points are from the near side. If the impactor population, the size-frequency distribution and the impact flux is the same at the far side as at the near side, then the calibration applies to the far side as well. But there are theoretical reasons to think the impact flux might be slightly different between hemispheres. The gravitational focusing of the Earth preferentially directs impactors toward the near side, and the specific dynamics of the near-Earth object population may produce slightly different impact rates in different directions. If the far side impact rate differs from the near side by even a small factor, the calibrated chronology function, when applied to far side surfaces, would give wrong answers. The ages inferred for far side features would be systematically off. And since the lunar chronology function is applied to other planetary bodies throughout the solar system, systematic errors in the function would propagate into age estimates for all of those bodies. The importance of far-side sample returns, specifically returns from surfaces whose crater counts can be compared to the returned sample's radiometric ages, is therefore not limited to understanding the Moon. It is a calibration exercise for planetary chronology throughout the solar system. Accurately dating far-side surfaces would verify whether the chronology function calibrated from near-side samples applies equally to the far side and, by extension, to other planetary surfaces. The Chang'e 6 samples from the far side, if their radiometric ages can be determined and if the crater density at the collection site can be measured, will provide the first far-side chronology calibration point. This is one of the most scientifically significant potential outcomes of the Chang'e 6 mission, and the analysis of the returned samples is awaited with great anticipation by the planetary chronology community. The Artemis III and subsequent crewed missions to the lunar South Polar region will also provide opportunities for chronology calibration. Collecting samples from surfaces of different ages in the polar region and counting craters in the same regions will add calibration points at the lunar South Pole, where neither Apollo nor any previous sample return mission has collected material. Let us now talk about what the long-term future of far-side exploration looks like. Not in the immediate Artemis program context, but in the multi-decade perspective of what sustained lunar exploration might achieve. The far side is one of the least explored major terrain types in the inner solar system. Despite extensive orbital photography from multiple spacecraft, Lunar Reconnaissance Orbiter, Kaguya, Chang'e orbiters, and despite the Chang'e 4 landed mission and Chang'e 6 sample return, the far side has received only a tiny fraction of the direct investigation that the near side has received through the Apollo program. The total surface area investigated by rovers on the far side, through the Yutu-2 rover on Chang'e 4, is measured in kilometers. The total mass of far side samples in terrestrial laboratories through Chang'e 6 is approximately 1.9 kilograms. By comparison, the near side has been investigated by 12 astronauts who spent a combined total of approximately 80 hours on the lunar surface, collecting 381 kilograms of samples from 6 separate landing sites spanning diverse geological terrains. The difference in the depth of investigation between the two hemispheres is enormous. Closing this gap, achieving a level of understanding of the far side comparable to what we have of the near side, would require multiple sample return missions from diverse far side terrains, multiple landed missions with rovers covering significant areas, and eventually crewed missions capable of conducting the kind of field geology that trained astronauts can do far more effectively than robots. The technology needed for sustained far-side exploration is largely in development. The relay satellite infrastructure, the landing systems, the communication systems, the radiation protection. The scientific motivation is clear and well articulated. The geopolitical dynamics, with China and the United States both pursuing far-side missions, create at least the motivation, if not the coordination, to accelerate the pace of far-side exploration. What a fully explored far side might teach us is hard to fully anticipate. The history of scientific exploration shows consistently that the most important discoveries are the ones that were not predicted. But the known scientific questions, the lunar dichotomy and why it exists, the composition of the SPA basin floor and whether mantle material is accessible, the detailed chronology of early bombardment, the radio astronomy potential, the ancient ice record in permanently shadowed craters, provide sufficient scientific motivation to justify sustained investment in far-side exploration, regardless of whatever unexpected discoveries may await. The Artemis II mission was a step, not the destination. A human crew flew around the moon and looked at the far side with their own eyes for the first time in more than 50 years. They photographed it. They described it. They experienced the silence of the communications blackout and the specific quality of the ancient terrain seen through spacecraft windows. They added their experiences to the small archive of human direct knowledge of this place. Future crews will go further, land closer, stay longer, sample more, understand more. The far side is not a destination that can be exhausted in a single generation of exploration. It is a world whose full complexity will yield only to sustained and systematic investigation that we are only beginning. What the Artemis II crew saw during their 30 minutes behind the moon was the beginning of a new chapter in that investigation. Not the whole story, not even the first chapter. The robotic missions have been writing that chapter for decades. But the beginning of the human chapter. The moment when human eyes returned to the view that only 20 humans had seen before, and found it as strange and as ancient and as valuable as ever. The far side of the moon has been waiting 4 billion years for someone to look at it carefully. We are barely starting. There is a specific image that the Artemis II crew photographed during their passage around the moon that has become one of the most discussed images of the mission. It shows the far side of the moon in the foreground, the ancient cratered highland terrain, pale and densely scarred, no dark maria, no familiar features that Earth-based observers would recognize, and rising above the lunar horizon, small against the black sky, is the Earth, a sphere, blue and white, visibly smaller than it appears from the near side, visibly whole. This image is not new in concept. The Apollo 8 crew photographed Earthrise, the Earth appearing above the lunar horizon, in December 1968, and that photograph became one of the most influential images in history, contributing to the environmental movement and to a global shift in how humanity understood its relationship to the planet. The Artemis II crew captured a version of the same experience with modern cameras from a trajectory that gave a specific angle on the far side that the Apollo missions had not. But knowing the concept does not diminish the specific image. It shows something that is objectively true, and that is easy to forget in the press of daily life. The Earth is small. It is alone. It hangs in a black sky above a barren, ancient world that has no air and no water and no life and no warmth except what falls on it from the distant sun. The moon has been there for 4.5 billion years, and the Earth has been visible from the near side for all of that time. But from the far side, the Earth was never visible at all. The far side has always faced away, always will. The Artemis II crew looked at the far side for approximately 30 minutes. In that time, they saw more of the far side with human eyes than any human beings had seen since the last Apollo mission around the moon in 1972. They saw the ancient terrain that no mare volcanism ever covered. They saw the crater density that speaks of billions of years of bombardment. They saw the South Pole-Aitken Basin in the contours of the southern terrain. They saw the sky without Earth. What they were looking at was the original moon, not the moon as it appears to observers on Earth, selected, presented, the near side only, but the moon in full, the complete object, the part that always faces us and the part that never does. The near side tells us one story about the moon, volcanic, resurfaced, shaped by the warmth of the radioactive near side mantle. The far side tells another, older, colder, thicker crusted, almost untouched by the volcanism that decorated the hemisphere visible from Earth. Together, the two hemispheres are one world, a world that has been orbiting Earth for 4.5 billion years. A world whose tidal locking hid half of it from human eyes for the entirety of our species' existence, until we built machines that could go there and look. A world that is still mostly unexplored, despite decades of robotic missions and 12 humans who walked on its near-side surface in a window of activity that lasted less than 4 years and has not been repeated since. The Artemis II mission was not the Apollo program returning. It was something new. 4 people from different backgrounds and different countries aboard a spacecraft built by different companies under different contracts than the ones that built Apollo, flying a mission with a different political context and a different long-term intention. It was the first step of a program that intends to establish not a footprint, but a presence, not flags and a brief visit, but habitats and rovers and extended stays, and eventually a continuous human engagement with the Moon that previous programs never sustained. Whether that intention is realized depends on decisions that have not yet been made, funding that has not yet been appropriated, technology that has not yet been built, and the sustained political will of nations and institutions across the timescales needed to achieve something genuinely lasting in space exploration. The history of such programs is not encouraging. The pattern has been ambition followed by contraction, vision followed by budget cuts, beginning followed by delay. Apollo itself lasted only 4 years of surface operations before the program was cancelled. The Artemis program is trying to build a more durable foundation. But the crew of Artemis II did what they did regardless of what comes after. They went, they looked, they came back. They added their 30 minutes of far-side experience to the small archive of human direct knowledge of that place. They photographed it with modern cameras. They described it with modern understanding. They carried with them the knowledge accumulated by decades of robotic exploration and brought human perception to bear on what that knowledge describes. The far side of the Moon is still mostly unknown. The South Pole-Aitken Basin may contain mantle material that would transform our understanding of the Moon's interior, but it has never been sampled by a mission specifically designed to reach the deepest and most ancient material. The radio astronomy potential of the far side, the ability to observe the universe at frequencies blocked by Earth's ionosphere, potentially detecting signals from the cosmic dark ages before the first stars, has barely been touched. The permanently shadowed craters may contain ice billions of years old that preserves a record of the earliest volatile delivery to the inner solar system, and we have only barely begun to characterize that ice. The far side is a scientific frontier. Not in the metaphorical sense in which that word is sometimes used to describe difficult technical problems, in the literal sense that it is terrain that has barely been visited and that holds answers to questions of genuine significance about our origin and our solar system's history. The Artemis II crew saw it. 30 minutes of direct human observation from a spacecraft window. Ancient, cratered terrain stretching to the horizon, the sky without Earth, the silence of the communications blackout. That silence, the 30 minutes when the spacecraft was behind the Moon and no signal could travel between the crew and the 8 billion people on the planet below, is perhaps the most striking aspect of the mission when you sit with it. 4 human beings out of contact with all of humanity. Not just out of radio contact, out of line of sight, the moon between them and everyone else. The only way to be more isolated would be to be farther away, and almost nothing goes farther than the moon that is also within reasonable range of returning. In that silence, they were completely alone with the moon, with each other, with the ancient terrain below them, with the specific experience of being in a place that almost no human being has ever been, and that most human beings do not think about from one year to the next. The far side of the moon has been there for 4.5 billion years. It will be there for another 5 billion at least, until the expanding sun reaches it. It has been waiting for someone to explore it seriously. The Artemis II mission was not that serious exploration. It was a flyby, a moment of transit, 30 minutes behind the moon before the trajectory curved back toward Earth. But it was human eyes, human memory, human presence in the vicinity of a place that needs to be understood. The next crew will go closer. The crew after that may land. The far side will yield its secrets slowly to rovers and sample return missions, and eventually to geologists in spacesuits who can pick up a rock and look at it and know what they are looking at, in the way that no robot can fully replicate. The Artemis II crew started something. They did not finish anything. The exploration of the far side has barely begun, but they were there. They looked. In a moment between the void of space and the ancient surface of the moon, they added 4 more human beings to the short list of people who have seen the far side with their own eyes. That matters. Not because human presence is required for every scientific observation, but because there are things that human beings bring to exploration that instruments alone cannot provide. The qualitative judgment of a trained eye, the ability to be surprised, the capacity to recognize that something is different from what was expected, and to understand why that difference matters. The experience of being in a place, not just collecting data from it, that changes your understanding of what that place is in a way that processed data cannot. The far side of the moon is waiting, ancient and silent, facing away from the Earth that made it tidally locked, that has watched the near side for billions of years, that has only recently learned to look at the side that faces away. What is there has been there since before life existed on Earth. What we learn from it will tell us something about where we came from, and what the early solar system was like, and how the worlds we live among were made. The answers are in the rocks and the craters, and the ice in the shadows, and the ancient impact scars that cover every square kilometre of that hemisphere. 4 people flew around the moon and looked at it for 30 minutes. That is where we are. That is how early it is. That is how much remains. The far side of the moon holds the answers. We are barely learning to ask the questions.